So, there's this thing about plane geometry that's always bugged me. Yeah, that one.
What's bugged you?
Given 2 points, there's exactly one line touching both of them.
Well,
Okay, fine. 2 distinct points. Given 2 distinct points, there's exactly one line touching both of them.
that bugs you?
No, that's fine. It's this other bit. Given 2 lines, distinct lines, there's usually exactly one point that touches both of them. But every now and then, there's no point on both.
When they're parallel, right. This can be fixed though, did you know?
Fixed? You can just change the rules of math like that?
Well, no, I won't take away the plane you know and understand, though I will start calling it the affine plane to distinguish it from the new one we'll talk about. Instead, I'll give you a new set of points and subsets of it called lines, in which there will be a perfect symmetry of points and lines. What I'm thinking of will be your old plane plus a bunch of new points and one new line.
Okay, hit me.
It's simple to describe, though not at first to visualize. For each possible slope m, so m is a real number, or m equals infinity, we add a new point to the affine plane. Let's call the point p sub m.
How does that help? Say L1 and L2 are parallel. They still don't intersect.
We don't just change our point set, each of our old lines gets a new point attached. If the old line has slope m, attach p sub m to it.
I get it. They're parallel exactly if they have the same slope m, which means that now they share the point p sub m. I can't say I like the picture much, though.
Let's come back to the picture later. For right now, are you convinced that I've solved your problem?
Well, I guess that any 2 distinct lines either have different slopes, so already intersected in a point, or they have the same slope, so intersect in a new point. Have I checked everything?
Not really. First, you should worry that two distinct lines might now meet in more than one point.
Seriously? Okay, fine. If they already intersected in a point, then they have different slopes, hence the new points added to the lines are distinct, so not shared.
You also have to worry that we might have broken the two distinct points to determine a unique line rule we started with.
We might have it that. Okay, here goes. If we start with 2 old points, they determine a line. If we start with an old point x and a new point p sub m, then there's a unique line of that slope m going through the old point x. What if we start with 2 new points p sub a, p sub b? There's no line with slope both a and b.
And yet, those 2 points need to be on a line.
So every p sub a, p sub b should be on this new line for any pair AB. I guess that means that all my new points should be on this new line.
Anything left to check?
Now that I have a new line, I want to be sure it intersects any other line in a unique point.
Does it?
Well, the new line has all the slope points p sub a, if I may call them that,
Nah.
and any of my old lines has some well-defined slope m, so these two intersect in exactly the point p sub m.
All good.
I'm still not happy with the picture. Also, what is this new plane called, and what am I supposed to call the new points in line?
It's called the projective plane, or more specifically, the real projective plane, RP2, though we won't talk about why, and the new points lie on the line at infinity.
Oh, so they're points at infinity. Why is that supposed to be a good name?
Well, watch what happens if you make non-parallel lines slowly become parallel. The point of intersection will fall off the boundary of the affine plane.
Okay, but what if it falls off in the opposite direction?
Very good question. We still need the point of intersection to limit to the point p sub m at infinity for the same slope m. We can only have one point for that slope, not one for northeast and one for southwest.
So even though you drew it like a circle, it's not really? Wait, I know this story. It's called identifying the opposite points.
It is indeed. Maybe you've seen things like a Mobius strip created this way. Let's start simple. If you take a rectangle and identify the left side with the right side, it curls up into a cylinder. However, if you identify the left side with the right side backwards, you get a Mobius strip.
Okay, I think I see where the projective plane is coming in. We're supposed to identify all pairs of opposite points. So it's like doing the Mobius strip identification twice. We're missing a couple of cases though, right? What if we do two identifications but with no reversals?
Then you get a torus, the surface of a donut. This is secretly where games like Pac-Man and Asteroids take place. Wait, never mind. Pac-Man only has tunnels from left to right and not up to down. So Pac-Man is on a cylinder, but Asteroids is definitely on a torus.
What about the last case, where we use a reversal in one identification and not the other?
Then you get what's called a Klein bottle.
There seems to be a bad circle on that Klein bottle where it's going through itself. Where did that come from?
Yeah, if you were an ant walking around on that Klein bottle, you'd notice when you hit that circle. Whereas an ant walking on the rectangle it left, teleporting whenever it passes through an identification, wouldn't notice. In this way, the rectangle is actually a better picture of the Klein bottle.
So what about the bad circle?
That's what you've just got to suffer through if you insist on trying to draw the Klein bottle as embedded in three-dimensional space, and without using identifications. It doesn't fit. Whereas you work with identifications, then it fits already in the plane.
How bad is it if you try to embed the projective plane into 3-space? I'm guessing it's worse.
Yep. Not only does it have circles that it's passing through twice, there's got to be a point where it goes through itself 3 times. This particular embedding is called a Boy surface.
Pretty smart boy. How old was he?
Werner Boy is 22 at the time.
Side note, why is it called RP superscript 2? Is it the second power of some space RP?
No, it just serves as a reminder of what dimension the space is.
Anyway, is this boy surface seriously the best picture you're going to give me of the projective plane? I'm not looking forward to understanding why 2 lines intersect in 1 point, etc. in this picture.
Honestly, that sounds like fun to me. But anyway, no, I'll give you a much easier picture to work with. Start with the ordinary plane, the affine plane, and place a sphere atop it at the origin, so they're tangent. You can make the sphere to have radius 1 if you want, but it doesn't matter.
Oh, I think I know this story. This is the stereographic projection, right? We use lines through the North Pole to correspond points on the the affine plane, to points on the sphere except for the North Pole. Or if we think of the affine plane as the complex numbers, then this lets us add the North Pole and call it infinity. Altogether, it's called the Riemann sphere.
What you're saying is correct if we wanted to construct the complex projective line, but it's not what we want to do right now to construct the real projective plane. Instead of drawing lines through the North Pole, we draw lines through the center of the sphere.
Oh, I think I get it. Each point on the plane corresponds to 2 antipodal points on the sphere. I guess you'll say that I make the projective plane by starting with a sphere and doing this 2-to-1 identification. The picture seems like overkill, though. Why do I need the upper hemisphere?
You don't, you can get rid of it, but you'll still have to deal with a 2-to-1 identification on the equator. And now we're back to the picture from before. We've got a disk on which we're identifying opposite points.
Okay, that convinces me that this sphere modulo this 2-to-1 identification. Did I use modulo right?
Sure.
Does indeed give us another picture of RP2. Is it supposed to be nicer to do 2-to-1 identifications everywhere instead of 1-to-1 mostly and 2-to-1 occasionally?
Well, it's always nice to avoid special cases. Like, if you're an ant walking around RP2, it's more obvious in this picture that you'd always think you were on a plane, rather than in a picture that involves teleportation from time to time.
Okay, back to our agenda items. 2 points determine a line, 2 lines determine a point. Why is that?
Before, we connected a point in the affine plane to the sphere center, thereby getting a 1D space in 3 space. Now, let's connect a line in the affine plane to the sphere center, thereby getting a 2D space in 3 space. When we intersect this 2D space with the sphere, we get a great circle.
Okay, I see it. Given 2 points on the sphere...
4 spots on the sphere in antipodal pairs.
Spots? You don't want to say points?
I want 1 point in RP2 to correspond to 2 opposed spots on the sphere.
That's a good distinction. Okay, given 2 points in RP2, so 4 spots in opposed pairs, there's a unique great circle going through it. Versus 2 great circles intersect in 2 opposite points.
Spots.
intersect in two opposite spots, so 1 point in RP2. Okay, great. I think I'm satisfied with the geometry of points and lines in RP2. But how about the algebra? Like if I want to write down the equation of the line through 2 points.
Well, we could work with these spot pairs. So we'd have unit vectors x, y, z on the sphere considered up to sign. But what's much more convenient is work with all non-zero vectors considered up to scale.
Oh, I see. It's the same space, because you can always scale a non-zero vector by 1 over its length, at which point it's on the sphere.
Yep. And now instead of points and lines in RP2, we work with the 1D and 2D spaces through the center of the sphere.
Two 1D spaces span a 2D space, and two 2D spaces intersect in a 1D space, since we're in 3 dimensions. Well, that's pretty clean. Hey, 1 plus 2 equals 3. Is there something we can do with the 2 space perpendicular to a 1 space?
Good catch. It's called projective duality. It gives a correspondence between points in the projective plane and lines in the projective plane. It's a very precise way to think about the symmetry between points and lines.
So the dual of a point is a line? What if I dualize all the points in a given line?
As we drag a point along a fixed line, the corresponding lines swing around its dual point.
We're getting sidetracked from my question about the equation of a line in the plane.
Well, let's do an example. Start with y equals x minus 2. Where is that in our 3D picture with the sphere?
I guess it will be convenient to have the sphere centered at the origin. That means that the plane, which was tangent to the sphere, is sitting below it. I guess that's the plane z equals -1?
Too much trouble. Call it z equals 1.
Sure. Okay, so the line is defined by 2 equations, y equals x minus 2, z equals 1. I guess I can parameterize it with t.
But now you're supposed to think about all scalar multiples of those vectors, since you don't want to be able to tell apart a vector from its multiples.
What's the equation of this plane that we're parameterizing with c and t? I guess it's y equals x minus 2z instead of just y equals x minus 2.
That's right. The main thing to notice is that your new equation is homogeneous, i.e. all the terms have the same degree. It used to have y and x of degree 1 and the constant 2 of degree 0, but now that's a term 2z, and it also has degree 1.
Why is being homogeneous important?
A homogeneous equation doesn't care when you scale all the variables by the same factor, which is good because we're supposed to not be able to tell a vector apart from its non-zero multiples when working projectively.
Wait, something sneaky happened. We started with points t, t minus 2, 1, and considered all non-zero scalings of that, which means that the last entry can't be 0. But when we consider the equation y equals x minus 2z, there, it is possible for z to be 0.
Good catch. These extra solutions at z equals 0 have snuck in as some kind of limit of the previous solutions. What does it mean for z to be 0?
In our 3D picture, it means the horizontal plane parallel to the plane z equals 1. It cuts the sphere and the equator. Okay. It's the line in infinity.
What happens to your equation when z equals 0?
Well, now it's just y equals x, i.e. it no longer cares what the intercept was. It only knows about the slope, which makes sense because my line y equals x minus 2z has 1 point at infinity on that equator, and that point was the extra one we added to every line of that slope. Also, I guess what's good about this homogeneous equation is that it gets me the right equation when z equals 1.
Right, and there's a simple trick to make that happen called homogenization. You take every term whose degree is lower than the max and multiply it by the right power of z to bring its degree up to the max.
By max, you mean 1, right? Or are we going to do this with more complicated polynomials?
Nice segue. Sure, let's do degree 2 polynomials.
Well, before we go projective, let's see what polynomials in x and y we're talking about. We can have terms of degree 2, of degree 1, and degree 0. When we make an equation out of them, there are 6 parameters.
Call it 5, really, because scaling such an equation doesn't change the set of x, y where it vanishes.
Wait, that sounds familiar. Is the space of conics a projective space?
Indeed it is. Maybe you remember that to make the projective plane, we considered vectors in 3D except for the 0 vector, and then we considered them only up to scale.
And here, the 0 equation would be too stupid, not defining a conic. So we leave it out, consider the remaining equations up to scale, and get a what?
An RP5. One of the reasons to count dimensions like this is that it suggests how many points we need in order to determine a conic.
5, apparently. Each required point eats 1 degree of freedom.
That's right.
I want to see that, but first, let's do the degree 1 version, lines instead of conics.
Always a good idea. What's the dimension now?
Well, 3 parameters, but they're up to a common scale. So this is exactly RP2 as we described it before. I guess the statement is that to nail down a line, we ask that it go through 2 points.
Which is, of course, true. To be honest, this dimension count business doesn't promise that there will be only one line, or conic or whatever, through a given number of points. Rather, it says that the space of answers will be 0-dimensional.
Oh, so instead of there being exactly 1, there might be exactly 17?
Right. All we can rigorously conclude is no continuous parameters.
Is it in fact 17 in this conics problem?
No, it's only 1, don't worry. I'll give you a hint on how to find the one conic.
Not yet. If 2 points determine 1 line, and 5 points determine 1 conic, what's a problem where the answer is 17, or some finite number other than 1 anyway?
Here's such a problem. How many lines are tangent to 2 circles?
4?
Actually, it depends on how you place the circles. You can get 0, 1, 2, 3, or 4 tangents.
Maybe I'll pause the video to think about that. Okay, after dealing with all that casework, I'm ready for your hint on how to find the unique conic through 5 points.
We want to consider a polynomial, some linear combination of x squared, xy, y squared, x, y, and 1, such that when we consider our point x, y, together with the 5 points x sub I, y sub I, if our x, y is equal to one of those 5, the polynomial vanishes.
Not much of a hint yet. You're just restating the idea that the conic goes through the 5 points.
Okay, I'll make it harder, which in mathematics often makes it easier. Let's demand further that the polynomial vanishes whenever any 2 of the 6 points, that is, the 5 control points plus the generic x, y point, coincide.
Okay, that does ring a bell. Determinants are like that. If any 2 rows of a matrix are the same, then the determinant vanishes. So I want my equation to be a 6 by 6 determinant?
Well, in the picture here, you've got a 6 by 2 matrix where 2 rows might coincide. Can you flesh it out to a 6 by 6 matrix?
I guess it's easy to do that? How much more do I need to remember about determinants? I don't think I learned a formula for 6 by 6.
Don't worry, all you need to remember right now is that there's a row expansion formula for determinants that works inductively. If you apply it to the first row here, you'll get x squared times some 5 by 5 determinant, minus xy times some other 5 by 5 determinant, etc. In particular, you will definitely get some conic, and it definitely goes through the 5 points.
Okay, it's definitely time for us to play with this a bit.
If you're really precise, you can get 2 crossing lines. That's when your degree 2 polynomial factors as the product of 2 degree 1 polynomials.
Could we maybe go back to the there's one line through 2 points version?
Oops, yes, good idea. In this case, it's a 3 by 3 determinant. 1 row for the variables and 2 more for the 2 points. Being only a 3 by 3, it's reasonable to expand it out.
Okay, that looks plausible. If we rewrite in y equals mx plus b form, it's got the right slope m. I want to get back to the projective plane and see what these conics look like on that sphere. But before that, I realize I'm curious about circles.
What about them?
There's supposed to be one circle through 3 points. Is there a determinantal way to make that? I guess a 4x4 determinant, 1 row for variables, 1 row each for the points.
Well, can you describe a circle using 4 parameters up to scale?
Maybe. It's a special kind of conic. That's only 3 parameters, but I guess I should allow for overall scaling. Okay, let's rewrite. And now we're looking at combinations of x squared plus y squared, and x, and y, and 1. I guess the only difference from the story before is that instead of working with monomials individually, we have x squared plus y squared as a block.
Now that we know the equations for conics, and more particularly circles, in the affine plane...
Right, how do we see them in the projective plane? We had this homogenization trick. Let's play with 5 points like we did before, but see what they look like up on the sphere.
Well, when you have an ellipse in the affine plane, what does it look like up on the sphere?
2 ellipses. Or whatever, some kind of spherical ellipses, if that's a thing. One antipodal to the other.
Down on the affine plane, it's a hyperbola. What about on the sphere?
It's 2 ellipses again. How is that? The hyperbola is disconnected. It comes in 2 pieces. Each of its arcs is getting me 2 arcs up on the sphere, one in the southern hemisphere, one in the northern. Oh, it's about the point at infinity in the northeast being the same as the point at infinity to the southwest. So when I wander off the end of my hyperbola, I come back from the other side, and now I'm on the other arc.
Let's phrase that in terms of a sphere. We start on one arc in the southern hemisphere. We go up to the equator, and then we keep going to a spot in the northern hemisphere. But because of our identification, that's the same as a spot in the southern hemisphere.
And if we keep going, we'll just walk around each whole spherical ellipse thing and get back to where we started.
So what's the difference between ellipses and hyperbole? Once we're in the spherical picture, that is.
They look a lot more similar there than they do in the affine plane, that's for sure. I guess it's just about whether the curve in the projective plane intersects the equator.
The line at infinity.
About whether the curve intersects the line in infinity in 0 points or in 2 points.
There's another case, you know.
They intersect in 1 point, i.e. our curve is tangent to the line in infinity. That's going to have to be the parabola case.
And so it is. One way to think of that, say looking at x equals y squared, is that the 2 ends of the curve are gradually becoming more and more horizontal.
They've got the same limiting slope, namely 0, meaning they're heading for the same point at infinity.
Say I give you a conic. How do you look at it and figure out whether it's an ellipse, hyperbola, parabola, or even something else?
Well, geometrically I know the answer now. It's about how this guy intersects the line in infinity. To be able to talk about points at infinity, I need to work in the projective plane. So I have to homogenize. But then I want to actually be on that line, so I set z equals 0. Now I'm looking for solutions to this quadratic, but it's in 2 variables.
That's because it's in 1 variable, but somebody homogenized it. Carry on.
Fine. I look at the discriminant and try to take its square root. If it's positive, then the curve meets the line in infinity in 2 points. If negative, they meet no points, and if 0, the curve is tangent to that line.
At this point, we have a pretty good handle of conics in the projective plane. One of the benefits of working in the projective plane is the duality between points and lines. What can this mean for conics?
Well, the connection between a point P and a conic C is that P might touch C. So maybe now I ask what lines touch C?
That turns out to be, not special enough. What's a more special connection between a line L and a conic C?
Oh, we could ask L to be tangent to C.
Go on.
Okay, each of these tangent lines to the affine plane is giving us a great circle on the sphere. Each such great circle is perpendicular to a line, pointing out a new point on the plane. Is that point tracing out a conic?
It is indeed. It's called the dual conic. There are some fun things to notice, like if your conic is an ellipse containing the origin, the dual conic is one too, with perpendicular axes. If yours is an ellipse not containing the origin, the dual conic is a hyperbola with the origin in one of its convex regions. But let's go back to that square root you used to determine whether a conic is an ellipse, a parabola, or hyperbola. What's going on in the case of negative discriminant?
Well, then I have to take square root of a negative number. Are we in the complex projective plane now?
Why not?
Wait, I'm having trouble counting. Before, we stuck the real affine plane into the real projective plane, adding only a little bit, one line to it.
The line at infinity, that's right.
So now I want to take the complex plane and add a little to it. I thought the complex plane was the same as the real plane.
Yeah, so what many people call the complex plane, I'm going to call the complex line.
What do line and plane even mean anymore?
To me, dimension 1 and dimension 2.
Then how do people get away with calling the complex numbers the complex plane? It's obviously one-dimensional. You need one complex number to say where you are.
Most people don't need to think about two-dimensional complex space, so they don't need to get the terminology straight.
Fine. For the next 3 minutes, the complex plane will mean C2, not C1, and it will have 4 real dimensions. Why are we worrying about this?
So we can think about where a circle meets the line at infinity.
Seriously. Okay, I'll bite. Start with the equation of a circle. Homogenize it. I don't have to expand out before doing that, do I?
No, this is fine. However, you scale in powers of z so as to get a homogeneous result.
Cool. Then look at the line at infinity where z equals 0. Now I get something where the only solution is x equals y equals 0.
The only real solution.
Right, I want complex solutions. Besides which, having x, y, z all equal 0 isn't allowed. Okay, let's scale x to be 1. Then y is equal to plus or minus I. So what?
You found the 2 points that lie on every circle.
What?
They're at infinity, and they're complex, but they're on your circle. You made no assumptions about your circle, just that it's a circle, and you found that these 2 points are on it.
You're probably going to tell me this is supposed to be intuitive.
Well, let's try this. How many points do you expect to see when intersecting 2 lines?
1,
Line intersects conic?
2, or 0, but I guess you'll just point me to complex points.
I will. Ellipse intersect ellipse?
4, I guess? Isn't it supposed to be the product of the degrees?
That's right. So why doesn't it work for circles?
According to Bezout's theorem, 2 circles should intersect in 4 points, but visibly they intersect in 2. So you're telling me there are 2 more.
And they are 1, plus or minus I, 0, which are points that lie on those 2 circles and on all others as well.
So you've convinced me that there are these 2 points that lie on every circle. Is the converse true?
What do you mean?
Earlier, we made the conic through 5 points. If 2 of the 5 are these special points, 1 plus or minus I, 0, is the resulting conic a circle?
Well, let's look at the algebra. Remember our equation. First, we'd better homogenize, and now let's plug in our special points as points 4 and 5.
I think I'm going to need a reminder about calculating determinants.
Okay, here's 2 tricks. One is you can add one row to another row without changing the determinant. Or subtract, or do it to columns instead of rows.
I see some simplification there. I'll subtract the 5th row from the 6th. And then add the 3rd column to the 1st to kill the 1 in the 5th row.
Sure you didn't do it to create x squared plus y squared in the northwest corner?
Little me?
Anyway, the other trick is that if you have a single entry in a row, you can cross out that row and column. It changes the determinant by a factor, but we don't care because we're setting the determinant equal to 0.
Okay, great. That negative 2i is right for this trick. Oh, cool. Now the trick applies to the negative 1, even though it didn't used to be the single entry in its row. Is that okay?
It is indeed. Recognize this 4x4 matrix?
It's the one we used to find the circle through 3 points back in chapter 3. Huh. Okay, one last question. If you try to make a circle through 3 collinear points, it makes a line instead, which I guess is a circle of infinite radius.
Is that the question?
No, it's that I'm worried about degrees. How did a degree 2 conic degenerate to a degree 1 line?
Well, let's look at it projectively and algebraically. What's happening to the equation?
We start with a times x squared plus y squared plus bxz plus cyz plus dz squared equals 0.
Can you guess what's happening to the coefficients in your infinite radius case?
Maybe the first term disappears?
That's right. What happens to the equation then?
Z factors out. So now there are 2 cases, either z equals 0 or bx plus cy plus dz equals 0. That second case is the line that I was expecting to see.
And the other?
Z equals 0 is the line in infinity, of course. So my circle didn't turn into a line. It turned into a union of 2 lines, one of which is the line in infinity, hiding there like a snake.